So now, our job, find all the solutions. And it might not be something we can factor. I mean, quite frankly, they have said, we know some of these are not going to be stuff that you can factor. Some of them you're going to have to use a graphing calculator to find and make sure they work and start that way. But in the end, we have to show some algebra. You know, we have to show some way that we know that they're going to work. Here's why. I put stuff in the calculator all the time. You guys have seen that. You know, you accidentally hit a button when you want another button, and you're looking at a graph and holding it next to somebody else in class and going, I got this. What did you get? You know, we have to know they're right. So we don't ever just trust the calculator that, oh, look, the calculator told me it's 4, 5, and 6, and go about our busy day. We have to say, all right, there's got to be some math I can do to check this. There has to be something that I know that these are going to work. And that's what we're going to work on in 5.5 and 5.6. Theorems about finding all the solutions, and solutions are also called roots. So we are going to use Carl Friedrich Gauss's fundamental theorem of algebra to solve polynomial equations with complex solutions. What that means is we're back to seeing some imaginary answers every once in a while. It's just going to happen. And we're going to solve equations using something called the rational root theorem. And we're going to use the conjugate root theorem. But boy, we are not doing all these things in one day. We are not. So what I've done is I've kind of split this up into pieces that'll make sense each day. We'll get a little bit of practice at it, and then we'll go on to something a little different each day, because these things are huge. The fundamental theorem of algebra. Here's every polynomial in the world, find its answers. That's a big deal. So we'll just focus on that today. And we have the fundamental theorem of algebra right here. And here's what it says in this book. Every book writes it a little bit differently. If p of x is a polynomial where its degree is greater than or equal to 1, so it has an x in it, then p of x equals 0 has exactly n roots, including multiple or complex roots. Here's what they mean. When we write down a polynomial, we will know how many answers it's supposed to have before we start. There's a really easy place to look, and that's the degree. And the degree is the highest power of the variable. So this polynomial will have 7 answers, 7 roots, 7 solutions, because roots are solutions. And it's our job to find them all if we can. Now, sometimes there aren't any real roots. Sometimes you graph it and it never crosses the x-axis. Well, we still do what we can to find the answers, and sometimes it gets a little messy. But the ones that we're going to give you, of course, on the test are ones that are going to work out a little bit nicer. So down here, basic question. When you look at these polynomials, how many answers, how many solutions, how many roots are these going to have? Look at A. How many answers should that have? 3. It's a degree 3 polynomial. Should have 3 answers. It might be that one's real and 2 are imaginary or something along those lines, but you should get 3. Take a look at B. 4. Highest power everybody sees is a 4. Yeah, this was in standard form already too. So when we think we're done, we need to know, hey, I put 4 answers down here because it's supposed to have 4. So the rational root theorem does this for us. The rational root theorem gives us a place to start. Back when dinosaurs roamed the earth and I was in high school, we didn't have graphing calculators. So we had to have a place to start. And that meant something we could do by hand to see whether or not things were going to work. And that's where the rational root theorem comes in. It says, you know what, we can give you some possibles, some things to try. And if they work, great. If they don't, we told you they were just possibles. So it says, when you have this as your polynomial, which is kind of scary looking, but don't worry about that too much. It's just saying start with the highest power and work your way on down. That's standard form. That's what we've already been doing. Let that be a polynomial with integer coefficients, so no fractions or goofiness, just going to have integers. There are a limited number of possible roots. We know that because the highest power tells us how many answers are supposed to be. Now, it says integer roots must be factors of a sub 0. And that's the constant in the back. And it says rational roots must have reduced form p over q, where p is an integer factor of that constant and q is an integer factor of the number that's out in front, that a sub n. So you look at that box, and my goodness, do they make that sound horrible. Here's what we want to write down. Possible roots come from factors of the constant over factors of, I'm going to put LC for leading coefficient. Factors of the number that's in the back when it's in standard form over any factors of the number that's in front when it's in standard form. That gives us a list to try. And like I said, we have graphing calculators, so we'll be able to narrow that down a little better. But back in the day, we had to take those possibles and we just had to try them and see whether or not they worked. So up here, using their example, 21x squared plus 29x plus 10. Here's what we do. We go to the back and we look at 10 and we say, okay, what are all the numbers that would divide nicely, integers that would divide nicely into 10? 1 goes in there, 2, 5, and 10. But the negatives could also go in there. So we put plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. That goes on the top of our fraction. Then we go to the bottom of the fraction. And that comes from all the factors of the leading coefficient. Well, this is in standard form, so that's the 21. So I think, what numbers divide into 21 nicely? 1, 3, 7, and 21. And then I look at all of the choices that I have for possibles. So I go through this the first time and say, well, it could be 1 over 1, so that'll be plus or minus 1. It could be 1 over 3, so it might be plus or minus 1/3. It could be 1 over 7, plus or minus 1/7. It could be 1 over 21, plus or minus 1 over 21. And then I start over, but I don't put a 1 on the top anymore, because I've already done that. So now I do 2 over 1, which is 2, and I would continue on until I had all of those answers written out. And like I said, our homework for this, 4 problems. That was all the teacher could give us, because we had to do everything by hand. We had all of these choices. You're not going to do all those by hand, because what we're going to do is we're going to grab the graphing calculator and narrow down the search. That's what we're going to do. But that's what we had to do. That's all we had. We had the algebra, and that was how we could do it. So this is always a good place to start, because, unfortunately, one of you might forget your calculator when you go to take the MCAs, or you might forget your calculator when you go to take the ACTs, and you're just going to have to go with it, you know. You'll have to do the math by hand if you can. So here's our process. We are going to list the possible rational roots. We're going to list them, but we're not going to do synthetic with every single one of them. Sometimes there's just too many. What we'll do is we'll use a graphing calculator to narrow down the search. And then we'll use synthetic division, because if we get a remainder of 0, we know it works. We know it's a root. It's an answer. And then once we have it down far enough to where we can factor it, then we're going to factor it, because we want to use the algebra. So that means I better get some graphing calculators out here. I'll just put them on the desk here, so anybody can grab one. Four today. Is that going to be enough, or should I get some blue ones too? Anybody else going to need one? All right. Away we go. So there's steps to this. It says we're going to use the rational root theorem, and we're going to find all the answers for this. What are the rational roots of 15x cubed minus 32x squared plus 3x plus 2? So first step, How many answers are we looking for? Should be 3. When we get done, we should have 3 of them. Second step, I would actually try factoring this first, because if we can factor it, that's the easiest way to get the zeros. But this one has 4 terms. And the only way I know how to factor stuff with 4 terms is factoring by grouping. I already checked, there's no greatest common factor. So I think, let's see, 15 and 32, what can I pull out of there? 3 doesn't work at both. 5 doesn't work at both. Nothing I can do with that, but I could take an x squared out. And in the back, I realized the only thing I'd be able to take out of 3x plus 2 is a 1. Do the parentheses match? This isn't factorable by grouping. It doesn't mean it doesn't have 3 answers. There's still 3 answers. It just means we can't do it that way. We would love to. That would be the fast and easy way, but we can't do that. So the next thing we do is we list possibles, things it might be. So possible roots. Well, that comes from the little fraction I had you write on the last page, which is all the factors of the constant. So I look and make sure this is in standard form, and I get down to 2. Oh, good news. There's only a couple of numbers that divide into 2 nicely. 1 and 2. Plus or minus 1, plus or minus 2. That's good news. Then it has to go over all the factors of the leading coefficient, and that's the number in front in standard form, and that's 15. So let's see, 1, 3, 5, and 15. And then I make my list of possibles. You're going to have to do this on the test, even though we don't have to actually go through and try to find them all. 1 over 1 would be 1. 1 over 3 would be 1/3. 1 over 5 would be 1/5. 1 over 15 would be 1/15. Now I'm done with the 1 on the top, but I have to go back through with the 2. So 2 over 1 would be 2. 2 over 3 would be 2/3. 2 over 5 would be 2/5. 2 over 15, 2/15. So those are the possibles. Now, like I said, in the old days, we would just start at the beginning of the list and keep doing synthetic until we hopefully got 3 of these that worked, or maybe even just 1 of them that worked. But we're not going to do that. We have technology on our side, so we're going to graph it. And we're going to put in, way up here, in the black, the original. So 15x to the 3rd minus 32x squared plus 3x plus 2. And we're looking for where does this cross the x-axis. So I'm going to try zoom 6. Maybe we'll see one. I'm going to check my table and see if there's something nice in the table. Oh goodness, I've got that set for pre-calc. There we go. Just do second graph. Go to your table. Oh, good news. 2 is nice. Did it look like it crossed in 2 other spots? It does look like it crosses in 2 other spots, right? So, the problem is they're not integers. If they were integers, we would see them in the table. So we start with the one nice one that we see, and that's 2, 0. And here's what we do. We do our nice and easy synthetic with 2 in the hopes that we're going to get a remainder of 0, otherwise we punched it in wrong. So I've got 15x cubed, negative 32x squared, 3x, and 2. They're all there. I don't need any placeholders. Now remember, what we want is we want a 0 for a remainder. A 0 for a remainder means it works. So go ahead and get started on your synthetic. Let's see if we can all get a remainder of 0. bring down your leading coefficient, multiply by a, add, multiply, add, multiply, and add. Is that good news? Yeah, we got a remainder of 0. That's good news. So what do we have left? Because this is one of those 3 zeros. We have to find the other 2. So let's see, this would be remainder constant x squared. 15x squared minus 2x minus 1 equals 0. And my hope is that it's factorable. You know, I saw 2 other spots up there. It looked like it crossed in 2 other spots. So this is not a nice one to factor. We're going to need to write down all the numbers that multiply to 15. 1 and 15, 15 and 1. I better write them bigger. 3 and 5, 5 and 3. And then in the back, the numbers that multiply to -1. That one's nice and easy. -1 and 1. Could be 1 and -1. I suppose we should write that one down too. But outside times outside plus inside times inside has to give us -2. That's how this works. So that doesn't make any sense to use 1 and 15. Those aren't going to be helpful. But 5 and 3, yeah, they're 2 units apart. So we'll check and see if we can get the -2. This would give us +3 and -5. There it is, 3 and -5. That adds to -2. So these are first times first. The other 2 are last times last. And we are super close to having those other 2 zeros. So 3x minus 1 equals 0. Means we'll add 1 and divide by 3. 5x plus 1 equals 0. Means we're going to subtract 1 and divide by 5. And we have all 3. Now the other thing I would do is look at that problem. That's going to be worth a lot of points. I mean, look at all the math we did in there. We did possibles, we did synthetic, and we did factoring. That's a lot of points. I would also use Blinky to make sure that my little 2 zero fractions there are right. Now, oh, the original black one. Here, let me put it up there. 15x to the third minus 32x squared plus 3x plus 2. Way back up at the original. All right, so second trace, number 2, and I'm going to put Blinky below the x-axis and hit enter, and then above the x-axis and hit enter. -0.2. That's 2/10. Doesn't 2/10 reduce to 1/5? There's our -1/5 answer right there. Second trace, number 2. I need Blinky above, enter, and then below, enter. 0.333333. What does that stand for? 1/3, exactly. So we know we're right. What we saw with the calculator and what we did by hand came out to be exactly the same thing. We have 1, 2, 3 answers. So notice how I had to do that mid-chapter quiz with you guys yesterday, because we have to remember all this stuff that we did on the last test, we can still use as we go to this test. Next one, not that that wasn't enough, right? Let's look at this one. How many answers should we get for this one? We better get 3 or we haven't found them all. So we try factoring. There's no greatest common factor, but maybe, just maybe, we can factor this one by grouping. Let's give it a try. What can we pull out of just the front 2? X squared, right? what could you pull out of negative 7x minus 6? That's it, negative 1. So any chance this is factorable by grouping? No, we didn't see the same thing in the parentheses. So we do have to write our list of possibles and then use the graphing calculator. So what numbers should go on the top of our fraction for possibles? 1, 2, 3, and 6. Yeah, those are all the nice integers that divide into 6. What's going on the bottom? We use the factors back here for the top. Where do we get the factors for the bottom? The first one. What goes into 2 nicely? That's it. This goes in the numerator of your fraction, which is the top. Those are all the numbers that divide into 6 nicely. 1, 2, 3, and 6. And then this is the bottom of your fraction. It's kind of backwards, you know? Yeah, just those. That's it. So now we're going to write them out. 1 divided by 1 is 1. 2 divided by 2 is 2. 3 divided by 1 is 3. 6 divided by 1 is 6. So I'm done with the 1. Go back for the 2. 2 divided by 1 is 2. We already wrote that down. We don't need to write that one again. 2 over 2 is 1. We already wrote that down. We don't need that one at all. Go back with the 3. 3 divided by 1, that's 3. That's in our list. 3 divided by 2, oops, that's not there. So we just add the ones that aren't already listed. So the 3's done. We go to the 6. 6 divided by 1, it's already there. 6 divided by 2 is 3. It's already there. There's our list of possibles. I don't even need this comma. Done. But I'm not going to make you do synthetic 2, 4, 6, 8, 10 times in the hopes that one of those works. We're going to grab the graphing calculator and we're going to narrow our search down. So we have 2x to the third plus x squared minus 7x plus 6. I hope that's a plus. I wrote over the top of it. Oh, it's a minus 6, isn't it? Somebody need that one yet? Of course. Because again, and it happens, and I feel so bad for the people it happens for. When people line up at the door for the MCAs and I have to clear their calculators, there's always somebody that says, I forgot my calculator. Well, if you forgot your calculator at home, you could do synthetic with all of these, and you could find one, and you would be able to do the problem by hand. You could. It wouldn't be fun, but you could. We do it because it's a possibility. We don't want anybody to miss problems because they didn't have a calculator. Alrighty, we got it in there?
So sure.
Zoom 6. Well, it's going to take away too. With the MCAs, though, you can have as long as you need to take the test. So, yeah, that doesn't matter. ACT, yeah, you got trouble. Yep. Any of these look nice? Kind of looks like 2, right? Maybe it's a 2 again. Second graph, there it is. Oh, we see another nice one though too, don't we? -1 is 0 and 2 is 0. So we could do synthetic with both of those. All right, we're going to try -1 and 2.
I got a bunch of numbers here.
Uh-oh.
I got 7.3, 6, something in there. I didn't know. Probably already have 5 minutes and 6 seconds.
2x cubed plus x squared.
Yeah, I'm 5 minutes.
Yeah.
So I'm going to take do my homework. Okay. See if you die. Yeah, so.
Oh, for goodness sake, you're at 154.
Nailed it. Don't know how
Alright,
we
I
have one
reset
thing.
your table.
Oh, thank you.
There you go.
That was fine.
Hey, 2 works, guys. Slam that 2 in here.
Pathway is second table set. third at zero. Alright, so we're gonna try -1 and 2 and see if they work. And I usually just do the -1 first. It doesn't matter though. You could do 2 first, you can do -1 first. 2x cubed, 1x squared, -7x plus 6. They're all there. Please pay attention because this next step is going to be real. After this, our next step is really important. All right, bring the 2 down. Multiply. Oh, we're just going to do synthetic on the original. Bring down the 2, multiply, add, multiply, add, multiply. Uh-oh, what did I do? 2, I was talking and I lost track of something. 6, 6. -1 is not going. That's why.
Obviously, I would hope so.
I had written over the top of it and then I put
That was
a
some work, right?
positive there. Now, here's the really important step. That one worked, so we don't start over. We keep going with these new numbers that we have down here. We're going to try the 2 in here. Because it worked, we're going to keep going with it. If it didn't work, we'd have to start over. Bring the 2 down, multiply, add, multiply, add. So both of those work. Haley.
How do you get -1? Because there's also another.
There, that's what I'm doing right now, Haley. See how we put -1 in there and we got a 0 for the remainder. So we just keep going with that because it worked.
So you do all the ones where the y equals 0?
Yes, that's what you do. Now, that's only 2 zeros. How many zeros was it supposed to have?
3.
3.
Yeah.
Well, that's okay because the last answer is right here. This says 2x plus 3 has to equal 0. That's a little bit of algebra. We have the answer. Subtract 3 from both sides. Divide by 2. And x equals -3/2, and we have all 3 answers. What we just did with the -1 and the 2 is called verifying synthetically. If you just write down the answers, you won't get the points for this problem. Because again, we punch stuff wrong into the calculator all the time. We have to verify synthetically and then use algebra on what's left. Now, you're right, these take a while. So I'm not giving you lots.
5 seconds. Perfect.
In fact, not all of those are start and finish problems. Some of them are just list the possibles. So they take a while, but I think I only gave you maybe one of these that's from start to finish. So see what you can do with that on this marvelous Wednesday. Away we go. This will after having a few Yeah, like I said, just in fact you can do all the ordering and everything online. You don't ever have to talk to anyone. But they do have really good customer service, so if you call them. Thank you. All right.